Hello, hello. Today we're going to be taking a look at a really good projectile motion problem here. It's related to the kinematics physics unit. I'm going to read through the problem, then we're going to solve through all these four different parts. These four parts that we're going to go through cover basically most of the items that we'll be asked to find in any projectile motion related problem. So definitely a good review problem here. One key note before we get started is that you should already have a good understanding of how to use the quadratic formula as well as how to use our trigonometric ratios. We will need both those tools in order to help us solve this problem. All right, so I'll read through the problem then. So a ball is launched from the top of a 25-meter high building with an initial velocity of 20 meters per second at an angle of 40 degrees above the horizontal. We're going to ignore air resistance. So part A is asking how long does it take for the ball to hit the ground? So this is actually going to be our total time, right? The total time in which the ball is in the air from the time in which it's launched to when it hits the ground. So basically the entire time it takes to go from here all the way down to here. B, what is the maximum height reached by the ball above the ground? So maximum height, we'll get more in detail on how to actually solve that when we get to that part, but that's represented by this section here, okay? We want to figure out the height from the maximum height in which the ball reaches with respect to the ground. So that'll be somewhere around here. Part C, how far horizontally from the base of the building does the ball land? So that's going to be our displacement in the x, right? That's going to be from here to here. I'll label that as our dx. And then finally, what is the ball's final velocity just before it hits the ground? So that'll be our final velocity, right? That'll be kind of some vector that's going down here. So we're given some information. Let's write down what we know. As always, let's also make sure that we draw out our compass to state our positive and negative directions. In this case, I've stated that north and east are my positive directions and west and south are my negative directions. So I'm told that we have a initial velocity, so our VI is equal to 20 meters per second, and that's going to be 40 degrees above the horizontal. So let's say the ball is launched in this direction, right? In the eastward direction, it's 40 degrees above that horizontal line. So the way I'll write that in vector form here is going to be east 40 degrees north. That's represented by this vector I previously drew out here. Okay? And I'll label that as my VI. Now with any kinematics problem, when we're dealing with two-dimensional problems like this one, we always need to split our horizontal and vertical components separately, right? So that being said, I'll classify this segment here as our initial velocity in the x, and this segment here as our initial velocity in the y. Okay, now to find that, right, that's kind of already given to me, but I need to actually find it, right? That's kind of one of the first steps we got to do. I know that this angle is 40 degrees, right? So like I said at the beginning, I need to use my trigonometric ratios here to figure out what VIX and VIY are equal to. So for VIY, I know that VIY, it's the opposite side with respect to my angle of interest here. So this 40-degree angle here, that's my angle of interest. So using my trigonometric ratios, I know that, right, I'll make a note up here in the side, that sine theta is going to be equal to my opposite side. So that's going to be VIY over my hypotenuse. So my hypotenuse here is just my VI, so I can multiply both sides by VI. So I'll get that VIY, our initial velocity, in the y dimension is going to be equal to our initial velocity, right? That actual value times sine theta. So that'll be 20 sine and 40 degrees is our theta. That's our angle, right? And also, that's going to be in the northward direction, right? This will be a positive value. Next, our VIX, which is going in the eastwards direction. I'm going to use my other trigonometric ratio. I know my VIX with respect to my angle of interest here, right? That's the adjacent side, so I'm going to use cos theta equals my adjacent side, which is VIX, over, again, my hypotenuse, which is VI. Multiply both sides by VI, right? So then I'm going to get my VIX, initial velocity x component, is going to be equal to my initial velocity, total initial velocity, so again 20, and then cos the same angle, cos 40, and that'll be in the positive or eastward direction. Okay, so now I've got all my values that I need for given my initial velocity. I'm also told that the ball is launched from 25 meters above the building, so this height here, right, this height here on the side, that's 25 meters, and overall, looking at it from our initial point to our final point being here on the ground, our object or our ball is displacing overall 25 meters downwards. It starts 25 meters above the ground, but overall, right, it's going to land on the ground. So in the end, it's actually overall coming down 25 meters, right, in the y dimension. So I'll just write that up here. My delta y is equal to 25 meters, my change in y, right? My change in position of my object in the y, right? 25 meters south, downwards. Okay. One other thing that I always know when dealing with projectile motion problems is that my acceleration in the y component, right, is always going to be equal to my gravitational acceleration, which is approximately 9.8 meters per second squared in the south or negative direction, right? It's going to be acting downwards on the ball. It's pulling the ball down. Okay, so now we've set up our problem. Got everything set up here. I've kind of we've drawn out, right, what we think the motion of our ball is going to look like. We've written down everything we know. Now we know what we got to solve. So part A, okay, part A, I got to figure out how long does it take for the ball to hit the ground. Okay, so I got to figure out how long it takes from the time it's launched, right? The time it takes from here all the way to here. So I'm going to look at my big five equations. I know that I have VIY, I've got DY, and I've got AY, right? I've got these three, and if I want to find my fourth variable, which is my time, okay, I can use the following equation. That's going to be our change in y. Again, we're going to use everything in our y dimension to help us get us that time, right? I can't, like I said before, I can't mix y and x components together. So I'm going to have my delta y equals my initial velocity in the y times time plus 1/2 times our acceleration in the y times our time squared. When inputting all of our values, it's very important that we kind of input our values in based on the vector, right? Based on the direction, based on the actual value. So if it's in our negative direction, right, I'm going to put it as a negative value. If it's positive, I'll leave it as a positive. So here, we'll start from here. I'm going 25 meters south, so I'll have negative 25, since south is my negative direction, right? Equals my initial velocity in the y. That's going north, so that's positive. The y is sine, so 20 sine 40 degrees times our time plus 1/2 times 9 point, or I'll punch that in, 1/2 times negative 9.8 times our time squared. I'm going to rewrite this so that it's in terms of our quadratic formula standard form. Okay. So then I'll set it as 0 equals, I'll take my t squared term first. This will give me 1/2 times 9.8, which will be 4.9 t squared. Then I'll have plus, and when I I'll just put it in my calculator, right? I'll just do that right now, get 20 sine 40, which will give me approximately 12.86 delta t, and then I'll move the 25 over, so then I'll have plus 25. All right, so now I've got some quadratic formula here. It's in standard form, so this is my, just a quick refresher. My standard form is ax squared, or 0 equals ax squared plus bx plus c, okay? So, right, in this case, my negative 4.9 is my a because it's got the t squared, right? X is just replaced by t in this scenario. My b is 12.86 and my c is 25. So I'm not actually going to write out the whole quadratic formula here. You could either use an online calculator or feel free to use the formula yourself and solve it. But upon, right, using the quadratic formula, we're always going to get two values. So the first value being t equals about 3.94 seconds, and our other time is going to be equal to negative 1.3 seconds. Important concept we should take away from this is that when dealing with any physics problem in general, we're never actually going to have negative time because negative time doesn't exist, especially when dealing with physics problems. So that being said, we should always assume to take our positive time value. Okay, so I got positive 3.94 here. Here I got negative 1.3. So, right, I can just write a comment or whatever and state that the actual time is going to be 3.94, right, since negative time doesn't exist, especially, like I said, in physics problems. Okay, question B is asking, what is the maximum height reached by the ball above the ground? So that's going to be this height here, right? Now, one very important concept to take away from this is that anytime you're asked to find the maximum height, okay, of our object in a projectile motion problem, we can always assume that at this point, at this instantaneous point here, the velocity in the y, okay, doesn't matter if it's the initial or final velocity, but the velocity in the y is always going to be equal to 0. And just very high level, that's because the ball is, right, the y component, it's moving up, then it's gradually kind of plateauing, and then right at this instant, now the velocity in the y is flipping from positive to negative. Now it starts to move downwards, right? Memorize that concept because you'll need it when asked to solve for the maximum height of an object in a projectile motion problem. So I've got some initial velocity, right? I know that, and I can basically say that if I'm comparing this point to this point here, I can essentially say that my initial velocity is equal to our, right, 20 sine 40, which we calculated already and got about 12.86. And that's going in the eastward direction, right? So that'll be positive. And then I have my final velocity, right? If I'm comparing this point to this point, right? That's what I'm doing. I'm taking the ball at this point and I'm comparing it to this point. So at this point, I'm going to say that the velocity, right, is going to be equal to 0. And these are both for the y components, right? I also know that the acceleration in the y, right, is always going to be this. Okay, for part B, right, same thing. It's just going to be 9.8 meters per second squared. So I can now use another one of my big five kinematics equations to actually solve for this displacement. But there is a little bit of a trick involved, so follow along carefully. The formula that I'm going to use is our final velocity squared equals our initial velocity squared plus 2 times the acceleration times the displacement. All these are vectors. Okay? So I know this is going to be equal to 0, right? We know that the final velocity, so I'm going to write 0 equals 12.86 squared plus 2 times negative 9.8 times our delta dy. Okay? So I'm just going to rearrange this now and solve for my delta dy, but there's one very important concept here, right? And that's this delta here. We didn't really talk about that earlier, but I'm sure you may have seen it before. This delta basically represents the change in. We can kind of classify that as something like this. So delta D being equal to our final displacement minus our initial displacement, okay? D2 minus D1 also works. It's the same thing. We're comparing the final to the initial. So in this case, I'm actually solving for this df with respect to the ground, knowing that my initial displacement, right, with respect to the ground again, is actually 25. I'm not going to put in negative 25 here, okay? I know I said here that, right, it's 25 south, but in this case, I'm not going to put minus 25. My DI is 25. I'm starting, right, at 25 when the ball is launched. I just want to find what that DF is. And this, solving it this way, will just give me a straight up answer for, right, our DF, which will essentially just tell me right away what that maximum height is going to be. So I'm going to make some space here. I'll move this around and we'll continue from here. So basically what I'll do is, let me rearrange this so that I have here, I'll have 12.86 squared, which gives me approximately 165.4 minus 2 times my negative 9.8 here, which gives me negative 19.6 times my df minus my di, which I said is 25. And I'll leave it like this. Okay? I'll rearrange this again so that I get 165.4, right? If I move this over, then I'll just have 19.6 times df minus 25. And then I can factor this in, rearrange, and solve for df. So I'll just multiply 19.6 by df and by 25, which will give me 165.4 equals 19.6 df minus 19.6 times 25, which is 490. Then I'll move this over to the other side, add it to 165. So on this side I'll have 655.4 equals 19.6 df. And then divide both sides by 19.6. And I'll continue up here. I'll get that my df is equal to 33.4 meters. And so that is my maximum height reached by the ball above the ground. So this height here, that's going to be 33.4 meters. And I'll write our solution to that up here as well. We could also just call this overall now dm, max height, which is 33. Okay, a little bit of a tricky one there, but remember the key thing is, right, to basically understand that our final velocity in the y component is going to be 0 there, and that we can compare our initial point to that point at that max height as like our final state and compare these 2 points to solve for what that distance could be. So I'll clear all this and then we'll solve for part C. Alright, so how far horizontally from the base of the building does the ball land? So that's going to be our dx, right? This distance here, our displacement in the x. So because there's no acceleration in the x dimension with any projectile motion problem, I can always revert back to my basic velocity equals velocity in the x equals displacement in the x over my time. And reminder that our time, right, our time is the one variable that can go between both dimensions. And I've already found the time, I've already found that total time, so I can actually utilize what I've already found in part A, as well as this Vx, which I've already put here, right, and rearrange my equation and essentially just solve for that delta x. So upon rearranging that, I'm going to get that my displacement in the x is equal to v of x times my time. Okay? So when I put that in, right, I'll have 20 cos 40. I'll just punch this directly into my calculator, right? 20 cos 40, multiply that by our time, which is 3.94. And when I punch that in my calculator, I'm going to get about 60.36 meters. And that's our answer to that. Very basic, very straightforward problem. One other important note that I didn't really touch on yet is that our velocity in the x dimension is always going to stay the same, right? It's going to be the same everywhere because there's no acceleration acting on the ball in the horizontal or x dimension, and because of that, with any projectile motion problem, we can always assume that this initial velocity in the x, it's going to be the same velocity at this point, at the final, right? Our v f of x is also going to be equal to the same thing as our vix, okay? And again, that's because there's nothing accelerating our object in the x dimension. Okay, d of x is equal to 60.36 meters. I'll clear this now, and then let's solve for our final part, okay? Part D. What is the ball's final velocity just before it hits the ground? Let's say, right, let's take this vector that I drew. Let's take this, okay? And the angle might be off, but that's okay. We're just kind of making a guess here that, right, this kind of vector, right, again, it's going to have, like our initial velocity did, we're going to have an x and a y component. And like I told you in part C, our vf of x, again, so we'll say that this is our final velocity. We need to solve for that. We know our vf of x is going to be equal to our vi of x, okay? Because there's no acceleration acting on the ball in the horizontal or x dimension, right? And because there's no acceleration acting on the ball in that dimension, then there's no way that the velocity can change. So that's why, right, we can just take this value and set it for that x component here. As for our VFY, right, our VFY, we are going to need to solve for that. So again, as always, I can refer to one of my big five equations. I already have a lot of variables that I've already solved for, but I'm just going to use probably maybe the easiest one here and say that our final velocity in the y, is equal to our initial velocity in the y, our acceleration in the y, times our time. So I'll plug in all my values. Our VIY was about 12.86. That's going to be positive, plus negative 9.8 times 3.94. And when I plug that in my calculator, we're going to get a final velocity in the y of about, right, negative 25.82 meters per second. Because it's negative, right, I could also rewrite this as 25.82 in the south or downwards direction. Okay? So I'll just write this up here, make a bit of space, and I've got my VF of x, and that's going to be about 15.32 when putting in 20, again, 20 goes 40 into our calculator, we're going to get about 15.2. That'll be still in the east, right? It's moving east. It's just our VFY is moving down, so that's south. Okay? And now, trigonometric ratios, right? We have two of these sides. I can solve for the third side using the Pythagorean theorem. So I can say that VF squared is equal to VF y squared plus VI x squared. Or I can just square root both sides, right? Cancel out the square root and the square here. So that I'll have V of f equals, I'll put this in here, 25.82. Doesn't matter if we put it in as a negative or positive because the square will cancel out any negatives anyways. Plus 15.32 squared. And square root of all that. When I put that in my calculator, I'm going to get an overall final velocity of about 30.03 meters per second. Okay, so this is just the magnitude, right? I'm actually asked to find the velocity. If I was asked to find the speed, that's it. That would be my answer. That's my final speed. But in order to find the velocity, I've got to give it some direction. Okay, so in order to do that, I've got to find what this angle is. I want to figure out what that angle is. That'll help me give me kind of this direction. Okay. And it doesn't really matter if you did it the other way too, you could solve for this angle as well, right? But I drew it this way, we're just going to solve for this angle, but again, it doesn't matter if you do it with that angle or this angle. So to find this angle, again, trigonometric ratios, I can use doesn't matter which one, I'll use my tan ratio to say that my tan ratio, right, is opposite over adjacent. So with respect to this angle, my VFX is my opposite and my VFY is my adjacent. So then, right, I'll take the inverse tan, which will give me tan, I 1 there, VFX, which is 15.32 over 25.82. Okay, and it doesn't really matter here if we put our negative or positive values. Again, it's just the values will be fine. We're just taking the ratio to give us an angle. And when I punch that in my calculator, I'm going to get around 60 degrees, okay? So, to finalize the problem now, I'm going to state that my final velocity is equal to my final velocity, right, that I've found here, so 30.03 meters per second. The angle's kind of coming off, right, this line first, so I'm going to say it's going south and then 60 degrees towards the east. And if you had gone about writing it or drawing it out the other way, you could have also had east 30 degrees south, okay? It's the same answer. All right. So a very good problem here. A bit of a long one, but we covered kind of all the different types of questions we could get out of a typical kinematics projectile motion problem. I really hope this helped. If you guys have any questions or comments, please let me know down below. And thanks for watching.